Okay, so hello everyone. Welcome back to your Comp 335 tutorial. This is tutorial 12, your last tutorial, and we're solely going to be talking about Turing machines today. So, what are Turing machines? What are they about? Well, let's find out. So, what is, first of all, the definition of a Turing machine? Well, we say that a standard, and this is very important to recognize because you're going to see in the course that there are Turing machines which we consider non-standard, but for the assignments as well as this tutorial, we're going to end sort of in general, when we think of a Turing machine, we're going to be thinking of a standard Turing machine. So what is a standard Turing machine? M, well, it's defined similarly to how we defined FAs and PDAs with a tuple. In this case, we have a 7-tuple with a few familiar symbols and maybe a couple of strange looking ones. So we first have, as usual, a set of states. So our Turing machine is composed of a set of states Q. Then we have an alphabet, sigma. We also have, instead of having a stack alphabet as we had in PDAs, we have an alphabet for our input tape. So this is for the input tape, which we're going to see in a second. Delta is our transition function. Now, our transition function looks a little weird. So what does it look like? Well, in this case, it takes a state Q, so let's say in your state Q, and it reads a symbol on the input tape, gamma, so let's say it's reading an A, and it goes to another state P, right? So it goes to another state P, replacing this symbol with another symbol from your input tape alphabet. Let's say it's B. And now, instead of saying, instead of having a push or a pop kind of instruction, we have an instruction of left or right. And this essentially tells us where to go on the, sorry about that, where to go on the input tape, okay? So what do we mean by the input tape? Well, actually what's going on really in a Turing machine, you're going to see an example in a second, but just a foreshadowing. Essentially what's going on is you're reading, as you usually did in an FA or a PDA, a string on a tape. So for instance, let's say you have A, B, A. But in this case, you're actually going to be using this tape to help you do computations. So what you now have is a pointer, in a sense. You have a pointer to the to a particular position on your input tape. And for the sake of the standard Turing machine, what we assume is that our initial, sorry, not our input, our initial state starts at the beginning of the string. Okay, so what do I mean by that? Well, I mean that if I have WABA, okay, then if I have my Turing machine, so it's a box, I know that I'm going to have an initial symbol, right? An initial state, sorry, I have Q0, my initial state. Then this initial state is going to correspond to the first symbol of my input. So it's going to start my pointer, which you can think of as being represented by my state. My pointer is at the beginning of the input at exactly A, okay? And then depending on this instruction here, L or R or left or right, I'm either going to go left, so I'm either going to take this pointer and go to the left, so go to the left here, or take my pointer and go to the right here. So let me just make sure it's not confusing. There we go. So I would go one position to the left, so this would be L, or one position to the right, so this would be R. Okay, starting at Q0. So again, remember this is for a standard Turing machine. In more sophisticated Turing machines, you can have a stay function or something like that, but for our purposes, we're just looking at L and R. Okay, and now we have a couple other symbols that we want to look at in our Turing machine definition. We have this new guy, the blank symbol, which essentially is everything that is not my input. So to the left of my input, you can just think of having an arbitrary length input tape, and to the left of my input, I'm just going to have blank symbols. Similarly, for the right, I'm just going to have blank symbols. So it's very similar to, you know, when you write a word. Let's say you write cat. On the left of that word, there's just a blank, and on the right of that word, there's just a blank. It's almost the same thing, except that here we're kind of being very explicit, and we're saying that each symbol holds a single slot in my input tape, and to the left I have blank slots, and to the right I have blank slots. Okay? So we already discussed what my initial state is. You know, you start at your initial state, and that initial state corresponds to the beginning of the input. And finally, we have the set of final states. A very important distinction from PDAs and FAs is that in Turing machines, a final state has no outgoing transitions. So in other words, if you get to a final state, you know, with the double circle, then you can't do something like, oh, well, if I'm here and I read an A, I replace that with an A, and I go to the right. So you cannot do this. Okay? That would violate the definition of the standard Turing machine. And finally, when does a Turing machine stop? So when does it end its computation? It ends its computation if there are no applicable transitions in Q. So for instance, if I have my Turing machine and I'm going through some states, and then I end up at a state that has no transitions, then at that point you would say that your Turing machine halts. And if it's not a final state, right, if it's not a final state, then you would reject that input. Another scenario could be you do have, let's say you have a transition AA goes to the right, but at that moment you're reading a B. Then again, there are no applicable transitions in your state Q, if this is Q. So again, your Turing machine would halt. And again, because it's not a final state, it would reject the input string. Okay, so I know I'm spending a bit more time than usual on this definition, but I think it's important just to get kind of our hands a bit dirty before we start looking at examples. But speaking of examples, let's look at our first one. So we have a Turing machine represented here. And in this first example, we're just going to walk you through essentially how the Turing machine computes when it receives an input string. So in this case, my input string is A, B, A, A. My initial state, so just not to confuse you, in this case, we just said our initial state was Q1. Typically it's Q0, but you know, it doesn't really matter what you label it. Just notice that this is my initial state. So what did we say about initial states and the relation to the input? Well, when we start at our initial state, So at the very beginning of our computation, we always begin at the beginning of the string. So this is why we have this kind of pointer here that can go either left or right, which at this moment, what it's seeing is it's seeing an A on its tape, right? So right now, kind of imagine that pointer has an eye, and the eye is seeing at that exact instance, it's seeing the symbol A, okay? So what can it do? What can the Turing machine do if it sees an A? Well, there's a transition for that. It says that if you're in Q1, right, and you're seeing an A, then replace that A with an A. So essentially, it's kind of like you're reading this A and then writing another A. So essentially, there's no difference in just keeping it the same. And we have our instruction to where to go. We have to go to the right. So essentially, what you're going to see in the next slide is that this Q1 is now going to go to the right. So the pointer is going to go to the right. And now it's going to transition to state Q2. So that's what happens. Now we're at state Q2, and our pointer, so our eye, is seeing B at the head of the input tape, okay? So what does it do now that it sees a B? Well, it checks, oh, do I have a transition where I have input B? Well, yes, it does. So if it sees a B and it's in Q2, then the Turing machine writes a B and again goes to the right. So in other words, it's going to read this B, write a B, so essentially no change, and then go to the right, okay? So it's going to end up in Q3, and it's going to be at this position in your input tape, okay? So this is what I meant when I said that the input tape is now part of the computation, okay? Because you're explicitly using directions on where to go with your pointer that's pointing on the input tape. So clearly you can kind of see already that this has a lot more power than a regular FA. And that's because you can essentially go back, right? You can go back and this is not going to get erased. So you could go back and check what you had. So there's kind of a sense of memory in this case, which an FA doesn't have. And as you're going to see in lecture, the type of memory that this has is even more powerful than a simple stack memory, okay? But for now, let's just keep going on this example. So we're going to end up in state Q3, which is going to now be pointing here, right? So that's where we're at here. Now what Q3 sees, it sees an A. So does it have a transition for an A? Well, yes. It says if it sees an A and it's in Q3, then it writes an A. So essentially replace this with an A, and it goes to the right. Okay, so it's going to stay in state Q3, but its pointer is going to move one sort of slot to the right. Okay, so that's where it is now. It's one slot to the right again. Again, Q3, its pointer is going to be reading an A. So again, what's going to happen is it's going to say, oh, well, I do have a transition for when I see an A. What I do is I see an A, or I read an A, I write an A. Essentially, I replace this with an A, so the same thing. And I go to the right. Okay. So what's going to happen is I'm going to go to the right to Q4. Actually, no, I'm not. Yes, I am. Yes, yes. Yes, I'm going to go to the right to Q. Oh, no. Okay, sorry. Sorry about that. Yeah, so I just confused myself. So your pointer is going to move to the right, but you're going to stay in state Q3. Okay, so that's a mistake that beginners and even TAs make is you have to distinguish between where you're at in the machine and also where you're at on the input tape. So in this case, I move my pointer to the right, so this is this direction, but because of this transition, I stay in Q3, okay? So now what's going to happen is I'm going to be in Q3, right? I'm in Q3, but now I'm reading a blank. So do I have an operation? Do I have a transition for when I see a blank and I'm in Q3? Yes, if I'm in Q3 and I see a blank, then what I can do is I can read that blank, write a blank, and then go to the left. So my pointer is going to go to the left, and now I'm going to transition to Q4, okay? Because I'm following this transition for the diagram, the state diagram, and I'm following this direction, the left direction here, for my input tape. So I'm going to go to the left. So now this is why I'm in Q4. I'm in Q4 and I went to the left with my pointer. So now I'm at A, but it doesn't really matter what I'm reading right now because I've finished at a final state. And so what happens is that M accepts A, B, A, A. Okay. So now let's see an example where we reject an input. So in this case, we have W is A, A, B, A. So why is this going to get rejected? Well, again, we start in Q1, and Q1 is going to be reading the first symbol on the tape. So that's going to be A. Then Q1 is going to say, oh, well, I have a transition for when I see an A. So what is that transition? What is that transition saying? It's saying that if you see an A, you read that A and you write an A, and you move the pointer to the right, and you also transition to Q2. Okay, so now you're going to be in Q2, right? So now you're here, you're in this state, and you're reading this on your tape. Okay. And now what's going to happen is Q2 is going to say, oh, well, do I have a transition that corresponds to me seeing an A on my tape? And in fact, if you check, well, no, it doesn't. It only can do something if it sees a B at the head of the pointer, right? Which it doesn't. And so because of that, because it has nowhere to go, the Turing machine halts. And because it halted in a non-final state, the Turing machine rejects A, A, B, A. Okay? And in general, this is going to be the language accepted by this Turing machine. And it's fairly obvious to see why, because if you start in your state Q1, the only thing that can allow you to move in your transition diagram is if you see an A at the first. So if you see an A at the beginning of your tape, then you can move to Q2. And then at that point, you need a B, right? So you need a B to go to Q3. And then once you're in Q3, you can read 0 or more A's, because as long as you get to Q3, you know that after a string, you just have blanks, right? So whether you have 0 A's, 1 A's, or any number of A's, Q3, once it goes through all these transitions, it is eventually, since it's moving to the right, it is eventually going to see a blank symbol, which at which point it's going to transition from Q3 to Q4, and then it's going to end in a final state. Okay, so you can see that any string that looks like A, B, A star is going to be accepted by your Turing machine. So in this case, of course, we could use an FA to accept this language, but here we're using the Turing machine kind of as an just to illustrate how it works. But in general, the idea of using a Turing machine to accept a language like this is kind of like using a supercomputer to compute a sum. Basically, it's kind of like a huge waste of resources because you can just use an FA, which is a lot less expensive in terms of resources. But we wanted to show you how essentially a run of a Turing machine would go. And I think we have kind of a similar example. So essentially, this is kind of a recall to your lecture slides, because in your lecture slides, if you remember, you designed a Turing machine that accepted the language A and Bn. At least I hope this was covered, because it usually is. And so what was essentially the idea for designing a Turing machine that accepted the language, the language AN BN for n greater than 0? Well, the idea was, let's say you have 3 A's and 3 B's. How is your tape going to work with this? Well, you know that you're going to start at the beginning, right? And you need to read an A. So you're going to read this A and say, okay, I've read this A. So you mark it with an X. Then you go through all your A's. And then as soon as you see a B, you say, okay, I have my corresponding B for my A, right? So I have my corresponding B for my A. So now what I can do is I can go back. I can go back and say, whoop, okay, I hit that X that I had just written. So I go forward, I read the A that corresponds to the second A in my string. So I mark that with an X. And then again, I move all the way to the B's, mark it with an X. And essentially what I'm doing is I'm saying for each A, there has to be a B. So that's why I'm marking an A, I'm marking a B, I'm marking an A, I'm marking a B, I'm marking an A, I'm marking a B, until essentially there is nothing to mark here anymore. So I go all the way to the end of my string and I have to see a blank. And if that does happen, if I do see a blank, then I can accept my string. Okay, so this is just a reminder of a review of how we could create a Turing machine to accept this language. So I think the Turing machine is also shown here. So just a reminder, let's say you had, well, actually, I think we're going to run through this example with slides. So let's do this. So let's say we had the input W, A, B, B. So remember what the general idea is you mark the first A, and then you mark the corresponding first B. You mark the second A, and you mark the corresponding second B, until there isn't anything sort of left here, at which point you go all the way to the end of your string, and you say, if you see a blank, so in other words, if you don't see anything else here, then that means you mark the same number of A's as B's, so you have something like AN, BN. Okay, so let's run through that in this example. So, so we have AA, BB, and we want to see how this gets computed by our Turing machine. So remember, Q0 starts at the first symbol in our input tape, so that's an A. So what happens is that A gets marked with an X, so this is why A is replaced with an X. Then you move your pointer to the right, so you move your pointer to the right, and you transition to Q1. So actually, maybe just so you can follow, let's do this. Yeah, okay. So, yeah, okay, so you're in Q0 and you're reading this A. So you read the A, mark that with an X, and move your pointer to the right. So you move your pointer to the right, and now you're in Q1. So now what Q1 does is it goes through all of the A's. So essentially it skips this A. So Q1 goes from here to here, right? The pointer, that is, goes from here to here. You're still in Q1. So that's why we're representing the state by the label and this kind of shape thing, this kind of shape as the pointer. So we're still in Q1, but now we've read that A and we've moved to the right, okay? So what happens next? Well, what happens next is that if you're in Q1, and you read a B, then what happens is you read that B, mark it with a Y, and go to the left. Okay, so that's what happens. This B got marked with a Y, and you moved your pointer to the left, and you transitioned to state Q2. Okay, so now you're in Q2. What happens once you're in Q2? Well, you read an A. So you read this A, and you move to the left, right? So you move to the left. And now you read an X with your Q2. And Q2 says that if it sees an X at the head of the pointer, then replace that with an X, and go back to the right. So now go back to the right and essentially start the process over. So now you're back in Q0. You're back in Q0, and now really it's the same thing. You go through the string again. You mark this A with an X, right, using this transition, and you go to state Q1. So now in this case, I'm going to be in Q1, right? Let's move this down. So now you're in Q1. You're in Q1. You're reading now a Y. So what happens if you read a Y? Well, you replace that with a Y and you go to the right. So replace this with a Y and go to the right. But you stick in Q1. You stay in Q1 in terms of the transitions. So that's why at time 7, this is what we have. Now you're in Q1 and you see a B. So this tells me, this transition here tells me that if you see a B, then you need to write a Y. So instead of this B, you write a Y, and you move your pointer to the left, and also you transition to state Q2. You transition to state Q2. So this is why now we're in Q2 and we're reading a Y. Okay, so let's move down again. So what's going on here? I'm in Q2 and I'm reading a Y. So this says that if I'm in Q2 and I read a Y, replace that Y with a Y and move my pointer to the left. So that's what I do. I move my pointer to the left. But because this is a self loop, I stay in state Q2, right? I stay in state Q2. And now I'm reading an X. So I'm in Q2 and I read an X. But now this tells me to replace the X with an X and go to the right. So move my pointer here, but also change states from Q2 to Q0. So now I'm going to be in Q0. So now I'm in Q0 and I'm reading a Y. Well, this is different, right? Because what was going on is we were reading A's, right? We were coming back to Q0. So this would be Q0. It would read the A and we would mark it. But now, so I don't know why I have 3 A's here. But now what's happened is you've marked all of the A's. And so Q0 is now reading this Y. So you're going to use the fact that now you're reading a Y to say, oh, well, this must mean that I'm not going to mark any more A's. So I'm going to go to the right. And I'm going to go a bunch of times to the right, reading my Y. So I'm going to go a bunch of times to the right, reading my Y. And what my hope is that I don't have any more symbols here. And in fact, I have the blank symbol at the end of my string, which would mean that I've marked the same number of A's as B's, which would mean that I'm going to accept the string. And that's essentially what happens. So Q0 sees a Y, it goes to the right. So now I'm in Q3. Q3 sees a Y, it's a self loop. So you stay in Q3, but you move to the right. But now Q3, let's move this down again. Now Q3 is reading a blank. Q3 is reading a blank. And so in that case, it's going to go to the left. By the way, it doesn't matter. I know in these examples, we're always going to the left, but at the end, you could also just go to the right. It doesn't really matter. So in this case, you read the blank, you go to the left, right? And you transition to state Q4. So now you're in Q4, which happens to be a final state. And so because you've ended, because your Turing machine halts in this final state, then what this means is that you accept AABB. Okay, and that's what you want it to do. So again, the analogy of using a supercomputer to compute a sum is kind of similar here, only a bit more sophisticated, because here we know that an FA could not, you can create an FA to accept this language ANBN due to the pumping lemma, and just intuitively due to the fact that it has no memory. But you could use a PDA, and in fact, you could use a DPDA, if I'm not mistaken. Yes, a DPDA to accept this language. So a Turing machine is still more powerful than a PDA. So it's still kind of using more resources than necessary, but it's not as bad as a Turing machine being used for something that an FA could do. So it's kind of like you went, if these are kind of levels of computational power, which I'm going to put in super double quotes because that hasn't been really defined formally in the course. If you have an FA, this is one level of computation, and you have PDAs, that's another level, and then you have Turing machines. So you're still making the Turing machine do something that a PDA could do, but it's not as bad as making a Turing machine do what an FA could do. Okay, just intuitively. Okay, so now an exercise for you. Try to design a Turing machine that accepts this language. So I encourage you to pause the video and to actually try this yourself. Okay, so hopefully you've had some time to think about this problem. So what's the idea, first of all, for designing a Turing machine like this? Because what do the strings that we want to accept look like? Well, they look like something like AA, for instance. For example, we would want to accept something like AA, B, 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 B. So to be honest, this is pretty similar to ANBN, and it's actually going to use a similar trick. Okay, so what's going to be the trick? Well, the trick is going to be, as usual, you start your computation at the beginning of the string, because the Q0 points at the beginning of the string on the tape. And essentially the idea is for each A that you're going to cross off, you're going to cross off two B's, okay? So you're going to cross off an A with, let's say, an X, go to the right, so go through these A's, and then cross off two B's with an X, and then go back, see, oh, okay, well, now I'm reading an X, so I need to go to the right. Go to the right, you see another A, so cross that off. Then go back to the right, go through those X's, cross off two B's, then go back, and then what you're going to notice is that you're just going to go through all of these X's and then end up here. Okay, so is this going to work? Not quite, is it? Because there's an issue here. So if you do use that logic, what if you had something like this, right? In which case you would start here, you would say, okay, cross this x, and then go here, then cross these two x's, go back, cross this x, cross these two x's, then go back. Oh, well, I hit an input tape, so I hit a blank symbol, so I must be done. So I accept, right? Well, no, of course not, because you have an extra b here. So the idea, similarly to a and bn, is you're going to want to use an extra symbol here. You're going to want to use a y symbol. Okay. So to be quite honest, initially when I was explaining this, so just right now, I thought it was x's, and then I realized that was a mistake. So I hope you caught that, and I hope you see why this would fail, but this would succeed, and that's actually what we're going to do. Okay. So let's clear this. Let's make this bigger. Okay. So how do you start this Turing machine? Well, students get scared when they try to design Turing machines. My first advice is, always try something. Always start by writing the initial state, because if you don't do that, then you're not going to get anywhere, right? And now you can, for Turing machines, really the idea is you want to get yourself a large enough example to see if you can create patterns within the Turing machine. Okay, and that's essentially what's going to happen here. So you're going to start in Q0. You want to read an A because your string looks like A and B2N. So you're going to read that first A, and you're going to cross it off with an X and go to the right. So you're going to do that. You're going to cross this off with an X. And now what you want to do is you want to skip through all of the other A's, right? So you're going to do that in state Q1. You're going to skip through all of the A's. So imagine just going through all the A's. And then, once you see a B, then, so once you see a B, then you want to cross this off with a Y, cross this off with a Y, and start going back to the left. Start going back to the left, and essentially you're going to want to go through all of your A's. You're going to want to go through all of your A's. You don't want to write your X's right now, so you're not going to touch your A's. Keep going to the left. So you want to keep going to the left until you hit the X that you most recently wrote. So until you hit that X that you most recently wrote, at which point you just rewrite the X, go to the right, and essentially restart the process. So, okay, let's restart the process. So essentially what happened is from Q2, I read an X and I went to the right. So now this is where my Q0 is, okay? So what happens? Well, I see that there's an A, so I can mark it with an X. So now I go to the right, so now I'm in Q1. But now notice that I've gone through all my A's, but now I need to go through this Y, okay? So I need to go through this Y. Okay, so hopefully some of you have seen a mistake that I've made. So what's going on here? So I'm going to go through my Y's, and then I'm going to get to my B, right? And then I see my B, I'm going to write it with a Y, and then go to the left, okay? So I'm going to go to the left and read through my Y's again. So I'm going to read through my Y's, so I need to add this, and then C and X, okay, C and X. And then, but now at this point, once I've seen an X and I've gone to the right, okay, once I've seen an X and I've gone to the right, then there isn't another A for me to read. So what I would do is I would now need to go through all of my Y's, right? So I would need to go through all of my y's. So I would go through all my y's, but then something weird happens. So I see a b, and that's not normal, is it? Because what should be happening is I should be seeing a blank, okay? Because I want to accept A, B, 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 right? So what's the mistake I made? Well, the mistake is instead of just reading one B, what I need to do for each A is I need to read two B's. So in other words, this transition should actually be moved to the right, and I should have an extra transition here that would help me go left, while this would make me go right. Okay, so hopefully everyone caught on to that mistake I made. So now let's see if this works. Okay. Again, it's very easy to get tripped up by these. That's why it's always good to make sure that you're following the input that you've committed yourself to very carefully. So let's see if this works. So you start in Q0, you read an A, so you write an X, you go to the right, and now you're in Q1. Now that you're in Q1, you're going to go through your A's. So you're going to go through your A's, there's no Y's, so now you go here, you read a B, so you mark this with a Y. So you mark that first B with a Y, and then you move to, let's say this is Q11, so you go to Q11. Again, you have to see a B, so you mark that with a Y. But now you go back left, so you go back left to Q2. You go through all your Y's, so you go through all your Y's. So now you're here, right? You're in A. Now you go through all your A's, so you go through all the A's. Now you go back to X, right? You go back to this guy. And so now you read that X so you go to Q2. So now you're in Q2, but now you're reading an X, so you're here. So essentially you transition to Q0. So let me clean this up. You transition to Q0 to this A here. And again, you repeat the process. You cross this A, you go through all your Y's, you cross two B's, you go back, you see that first X, you go to the right, but now up in this case, you're reading a Y. So now you're going to use this transition. You're going to go through all your Y's. And now, indeed, if you go through all your Y's, you're going to see a blank at some point. And then once you see a blank, you can go to your final state and accept A, B, 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 B. Okay, so yes, this does work. And it's very important to realize that it's essential for these two transitions to exist. You couldn't have just used one like I did before, because that would just give you A and B and again. Okay, so I hope that's clear. Yes, so now this is a different kind of exercise where we want to kind of read the input to a Turing machine. Okay, so maybe take a few minutes, pause the video and try this yourself. Okay, so hopefully you had a bit of time to look at this exercise. Let's see what's going on here. So we have this Turing machine, and we want to see if each input here is accepted or rejected by the given Turing machine. Okay, so let's start with the first one. We have AABA. So remember AABA, when you read an input string from your Turing machine, your Q0 starts at the first symbol of your string. So if you're in Q0 and you read an A, well, this tells you to go to Q1 and move your pointer to the right. So then once you're there, you need to, once you're in Q1, you will either need to see a B or a blank. And you don't have either in this case you're reading an A. So immediately your Turing machine halts at Q1, and because Q1 is not a final state, the Turing machine rejects, whoops, you did not see the A there. Turing machine rejects AABA. Okay, so this one would be a no. Okay. Let's look at B. So what does B say? B is B cube A. So we have B, 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 A. Okay, so again, you're in Q0, but in this time you're reading a B. So if you read a B, this tells you to go to Q4 and go to the right on your pointer goes to the right. Then once you're in Q4, read B's any number of times, and for those any number of times, go to the right. So you read this B, and you go to the right, then you read this B, and you go to the right. So you're still in Q4 at this point, but now you're reading this A. You're reading this A, so you're going to use this transition to go to Q5 and be at a blank symbol, okay? You're at a blank symbol, so you're at a blank symbol, but most importantly, you've essentially ended up in a final state, which has no more transitions, outgoing transitions. And so the Turing machine halts. Again, it halts. But this time, because you've ended up in a final state, it accepts BBBA. So this one is indeed accepted. Okay, let's look at C. So what is C? C is A, B, 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 A. Okay, so this one would be, you're in Q0, then you read an A, so you go to Q1. You read B's any number of times, moving your pointer to the right. So you read that first B, you move to the right. You read that second B, move to the right. You read that third B, move to the right. Now you're in Q1 and you're reading an A. Again, it's the same problem as before. Q1 doesn't have any transitions for when it sees an A. So your Turing machine halts at Q1 because Q1 is not a final state. It rejects A, B cube, A. So this one would be rejected. Okay, finally, let's look at ABB. Okay, so what happens in ABB? Okay, so here again, you're in Q0, you're reading an A. So you move to the right. You're reading a B in Q1. So you read a B in Q1, meaning that you're going to use this transition to move your pointer to the right, but stay in Q1. So you stay in Q1, now you're reading this B. Then again, you stay in Q1, but you move to the right. And now you're reading a blank because anything to the left and to the right of your input string on the tape is blank. So now you're in Q1 and you read a blank. Well, this transition tells you that if you do read a blank, you can go to Q5. So you go to Q5, so you actually you move to the right, so you're on the second blank. And now, because your Turing machine can't go anywhere else, right, it doesn't have any more transitions to use, your Turing machine halts, okay? And because you end in a final state, your Turing machine accepts Q5. Not Q5, sorry. Come on. Accepts ABB. Okay. A question for you, which you're going to actually see in lecture. What do you think would happen if you were to do something like this? Okay. So would you be able to accept any strings? Okay. This is not this seems like a trivial question, but it isn't. Okay. So you're going to see a kind of a loop like this where you're going to notice that this could cause an infinite loop. You're going to see that in lecture, and it's also going to be related to the very famous halting problem. Yeah, I'm just going to leave this as a question. And if you happen to want to answer it and you want to confirm the answer, you can email me or any one of the other TAs. Well, maybe not. Maybe the other TAs won't be expecting this kind of question. So maybe CC me if you do email the other TAs, so they know what's going on. Okay, but this is for you as kind of homework or just an exercise. Try this. See if you would be able to find a string that gets accepted. Okay. All right. So this is very much related to the previous question. So it's exactly the same Turing machine, but in this case, we want to know what the language accepted by the Turing machine is. Okay. So again, I encourage you to pause the video, and we'll look at the solution together. Okay. So hopefully you had a bit of time to try this exercise out. So again, as I mentioned before, the Turing machine is essentially the same as the one that we were looking at before. Now we just want to look at the language accepted by the Turing machine. Okay, so well, here we kind of see that there's kind of a natural way of expressing this as kind of the union of two languages. So we can see you can either start with this branch, or you can either start with this branch, but you can never sort of crisscross between branches, right? So what's the language that corresponds to this branch? Well, you start with an A, and then you can have any number of B's. So it could be either no B's, 1B, 2 B's, right? Any number of B's, right? Because you would read that A, you would go to the right, then read any number of B's, and then once you're done reading all the B's, you would finish with a blank, and then the blank would allow you to go to your final state. So clearly we have A, B star, right? So I hope everyone agrees with that. Now it's going to be unioned with something else. So what's that something else? Well, it's going to be this branch here. This branch here. So we know for sure that that branch corresponds to a language that starts with B, for sure. Then this tells us that we can have any number of B's, right? Any number of B's. Then we can go through all the B's, and then we can end with an A, right? So is this right? It looks right, doesn't it? But let's see, what happens if I have something like B, B, A, B? What happens in the Turing machine? Well, the Turing machine starts with this B, right? Reads it from Q0. From Q0, you go to Q4. So it reads this B, right? Now you're in Q4. B4 tells you to read the B and go to the right. So you're still in Q4, but now you're reading an A. So you read an A, you go to the right, and you're in Q5. Okay, so you have a B at the top, sort of at the eye of your pointer, at the head of your pointer. So this is very important because it's very different from PDAs and FAs. The fact that you don't finish your input does not mean that you're not going to accept. So it doesn't mean in general that you're not going to accept, because I don't care what's after this, right? I don't care what's after this transition from A to here, because as soon as I have a transition from Q4 to Q5, once I'm in Q5, Q5 is kind of like a halting state, right? Because it has no transitions. So once you're at Q5, your Turing machine just stops computing stuff. But because you ended in a final state, it accepts, okay? So it doesn't matter what's after the A here, essentially. Doesn't matter, it could be blank, it could be a B, it could be A, B, 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 it could be a nice palindrome, a prime number of A's, it doesn't matter, who cares, right? Because so long as you've ended up in Q5, which is a final state, and your machine halts, so long as you halt in a final state, your Turing machine accepts that string, okay? So that means that this is partially correct, but it's not entirely correct, because what we should write is after A, you could have any string, essentially, okay? And this is something that is not super obvious if you look at it for the first time, but if you wanted it to be B, B star A, then what you would have had to do was you go to AAR, right? Then you go to an intermediate state, you read a blank, right? So this would be this transition. Then you read a blank, and then you go to the right, let's say. So this forces the input to stop at A. It forces you to not have anything else, because if you do have anything else, you're not going to be able to go to your final state. All right. So I hope that's clear. I know this example was probably a bit surprising, because certainly if you're seeing this for the first time, it's not obvious. It's not trivial, but hopefully now that you understood the concept, if you get another example like this, another question like this, you won't fall into this kind of trap. Okay. All right. So I hope that's clear. So the next two exercises are going to be a bit more challenging for me to explain, because they're going to be having to do with creating Turing machines for actual languages for which there are no PDAs, so that aren't context-free. So this is going to be a bit more challenging to explain. Hopefully I'll do a good job, but as usual, I encourage you to pause the video and to try this one yourself. Okay, so hopefully you had a bit of time to scratch your head and see what's going on in this example. So we want to design a Turing machine that accepts essentially a language n A's, twice the number of B's, and then again n C's, right? So clearly there does not exist a PDA M such that L of M is equal to L, because L is not context-free. And of course, if you wanted to prove this rigorously, you would need to do this using the pumping lemma for context-free languages. Of course, I'm not going to go through that. I'm not going to put you through that again, but this is what you would need to do to sort of point out that, you know, if this is the set of languages accepted by FA, so in other words, it's a set of regular languages. If this is the set of deterministic context-free languages, this is the set of context-free languages, then L here, L is outside, L is over here, okay? So the hierarchy gets a bit even more complicated here, but you're going to see that in lecture, right? So what's the idea here? What's the idea? Well, let's take an example of a string that we would accept. So let's take A, B, 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 C, C. So what's the idea? It's similar to A and Bn, where you're marking an A with an X, marking a B with a Y, except that here, you're going to mark an A with an X, move through your A's, then mark two B's with Y's, move through your B's, and then mark a C with a Z, and essentially go back and go again, essentially loop. So mark this A with an X, go through your Y's that you already wrote, then mark these two, go through your C, mark the last C with a Z, go back, and then notice that there are no more A's to write. So then go forward, and notice there are no more B's to write. Go forward, notice that there are no more C's to write. So essentially you have a blank state, and so accept. So that's the idea, right? So easier said than done, of course. So let's actually create the transition diagram that corresponds to this Turing machine. Okay. So I really hope I don't confuse anyone here. So that's why I'm going to make sure I don't make a mistake. Okay. So as usual, we start in Q0, right? And so what do we need from Q0? We need Q0 to tell us that it sees an A and it writes an X. So Q0 is going to see an A, write an X, and move to the right. So with this, it's going to go to Q1. So now I'm in Q1, right? And now once I'm in Q1, I want to go through all my A's. So I mark this one with X. So I want to go through all my A's. Okay. So once I go through all my A's, what should happen is I should see a B. So I should see this B, write a Y, and now I don't want to go to the left yet. I want to go to the right again. And again, I want to make sure because I want to cross off two B's, right? So I'm going to cross off this one, and I'm going to also cross off this one. So that's going to correspond to seeing another B, writing a Y, and going to the right again. So now I'm going to go through all my B's, going to go through all my B's, going to the right, and then hope to see a C. So if I do see a C, then cross that with a Z, and now start going to the left. So and now I'm going to go to the left. So what I need to do is I need to go through my B's, right? Go through the B's that I didn't look at yet, then go through the Y's that I wrote, go through the Y's that, oh, whoops, this should be a left. Go through the Y's that I wrote, then go through the A's that I didn't look at yet, right? Go through the A's I didn't look at yet. And then once I see an X, so once I see an X, then I don't change the X. I essentially just start the process over. Essentially my Q0 moves to here, okay? Now this has become a mess, so we're going to clean this up a bit. Yes, very good. All right, so now I'm in Q0. Hopefully some of you see that this isn't complete yet, so that's why I'm going to go through another run. So I'm in Q0 now. I read another A, so I'm going to cross that with an X. So now I'm in Q1. So now I'm in Q1. But now I don't want to get stuck here, right? Because if I just left it here, I would halt and I would unfortunately reject. So what I need to do is I need to say that if I also see Y's, so if I also see Y's, then I don't touch them, but I go to the right. So I go all the way to the right until I see a B. Once I see a B, I can cross that off with a Y, go to the right. So I'm here now. Again, I need to see a second B, cross that off with a Y and go to the right. So now I'm here. So now, yes, I need to go through all my B's, but I also, because I wrote Z's, I need to go through all my Z's. Don't touch them, but just go through all of them until you hit the next C. So now you've hit the next C. And now essentially you're going to want to backtrack. So are you able to backtrack if you're here? Can you go left? Well, no, because you have B's, Y's, and A's, but you don't have the transition for if you want to go back for Z's, right? So you want to add that guy, add the transition for Z's, and now go back. So now let's clean this up. Oh, whoops. Yeah, okay. I don't want to. Come on. All right. Okay, let me erase this. I'm sure no one wants to think of the pumping law. Well, that's a nice lemma. All right. So now I'm here, right? So essentially what's happened is I've gone here, right? I've written this C to a Z and I've gone to the left. So now I'm going to go through all my Z's, right? I'm going to go through all my Z's, then go through all my B's. There's no B's, so I'm going to go through all my Y's, then go through all my A's. There's no A's, so actually what's going to happen is I'm going to go and see this X. I'm going to use this transition to go to the right. So now this is the situation similar to A and BN where Q0 expects to see an A here, but it's done crossing off the A's. So now what I need to do is I need to add an extra transition to say, oh, well, in that case, you're probably going to see a Y. So in that case, go to the right. That case, go to the right. Go to the right a bunch of times, reading all my Y's, right? Because I want to essentially scan all of this, making sure that I haven't missed a Y, right? So what should happen is that at this point, I should see a Z, okay? So I should see a Z and move to the right. And again, go through all my Z's, moving to the right. And so finally, if I move through all my Z's, what I should see is I should see a blank. And then once I do see a blank, then finally, yes, I can accept. Okay, and notice that I've explicitly used a transition here and a transition here because my language is AN, B2N, CN for N strictly greater than 0 because as was discussed in lecture for standard Turing machines, you typically don't really look at the empty string for standard Turing machines. So typically it's not considered. So that's why we were considering the language for N strictly greater than 0. So that's why we want to at least have read one Y. So essentially, actually, we want to at least have read 2 Y's and a Z. So then that would guarantee that we at least have A, B, B, C. Okay. So essentially that, I'm just saying essentially that this and these two transitions were required because we wanted to guarantee that we wanted at least one a symbol. At least one symbol for A and at least 2 for B and at least 1 for C. Okay. So hopefully that example, although I know it's not obvious, hopefully now it's a bit clearer with using this kind of method. This is kind of a good method to solve these types of questions. Using kind of a long enough example to kind of find these edge cases here that you would typically miss if you just ran through it once. So if you find a long enough example and you go through it, typically it's going to make your Turing machine succeed. Okay. All right. So I think we have one exercise left. Oops, sorry. We have one exercise left. Yes. Okay. So we want to design a Turing machine that accepts the language W, C, and W. So what is this? Essentially, it's anything that looks like A, B, B, C, A, B, B. So you have the same string on both sides of C. Okay, so again, I encourage you to pause the video and check back with me with kind of a going through the solution together. Okay. All right. So I hope you guys had a chance to try this this question out. An interesting exercise. Another interesting exercise that you could have tried was proving that Yes. I don't want to say anything wrong. No, I most certainly think that this is, in fact, not context free. So just want to make sure. So what could be a possible string? You could maybe try this. And yeah, so anywhere you pumped, so if you pumped here, you would get a different string. If you pumped here, you would get a different string. You pumped here. Yeah, so it looks like if you kind of scan through your whole string, looks like if you pumped anywhere, you wouldn't get WCW. So you could get a contradiction in any case, and so this would be not context free. So I'm pretty sure that this string would work. Again, don't quote me on this because I haven't actually thought about this, but I feel like this would be a good candidate for a pumping lemma. Okay. Okay, so we know that we can't use basically a PDA or a context-free language to either accept or generate this language. So we do in fact need to resort to a Turing machine. Okay. And so how do we do that? So let's make this bigger. Well, what's the idea? Well, let's say we had, like before, that string, which I hope some of you tried to make the Turing machine with. So what's the idea? Well, essentially what you want is you want to say for each symbol that you see on the leftmost, on the first part of your string, you want to see on the second part of your string, and they have to match their positions. So essentially you want to cross this A off with an X, and then cross this A off with an X. And surprisingly, unlike the other case, it's actually going to be enough to just use one symbol X. So you can cross the B off with an X, cross the B off with an X, then cross the B off with an X, cross the B off with an X. And then once you get to C, you just have to go through the right half of your string, make sure that you haven't missed any symbols, and then end once you see a blank. Okay, so that's the idea. Okay, so I hope some of you kind of had that intuition. If you didn't, that's totally fine. These are definitely not the easiest examples, but hopefully once I show you this, and once you practice a couple more on your own time, you'll be a bit more comfortable with designing Turing machines. Okay. All right. So what's the idea? Well, once you're in Q0, you actually have two cases, because here, yes, you could have an A, but you could just as easily have something like B, A, A, C, B, A, A, right? So in that case, you have two cases. You can either read an A, mark that with an X and go to the right, or you can read a B, mark that with an X and go to the right, okay? So let's stick with this example, but it's kind of an FYI that you could also start with B. Okay, so you mark this with an X. So now what do you want to do? Well, you want to go through the rest of your string. So the rest of your string is over AB. So what you would want to do is you want to go through the A's and go through the B's and go to the right. So you want to go to the right here. And then once you see your C, you can go to the right. And in this case, once you're in this state here, because you read an A, then right after you see what must happen is you must also read an A. So you must read an A, cross it off with an X, and go to the left. Okay, go to the left. In this case, if you go to the left, then you immediately see a C. So you immediately see a C. So that C you can use to go to the left. And then once you're here, well, you want to go back through all of your A's and B's. So that's what we're going to do here. Yeah, I didn't pick a good position for this. Sorry about that. So let's go like this. We're going to go through your A's left and through your B's left. Okay. And then once you finish going through all of these, once you see an X, then what you should do is you should say, okay, well, I actually have to start this process over, go to the right, and essentially reset my search at Q0, the next symbol that I haven't crossed off. So, well, what does that look like? So that looks like, so my A, I crossed with an X. My A, I crossed with an X. And so now I'm here, right? I'm in here and I'm in Q0, okay? So I hope everyone's aware that there are some transitions missing here, but that's part of the process. We're gonna get to them in a second, okay? So in this case, in Q0, you see a B, so now you have to use this path, this branch, to cross this X off. So you cross this X off, and now you essentially, it's kind of symmetric to what you would do with an A. You would go through the rest of the first half of your string, which is composed of A's and B's. And then at some point, you would have to read your C. And now, well, what you would have to do is, because now you've started writing X's, well, you have to read through your X's. And in fact, we can update this guy because it's kind of a symmetric branch. We can also update it here to say that the same situation would have to occur. So you would read through the X's that you already wrote. And once you're done those, then what must happen, because you're on the branch for B, what must happen is you must read a B and replace that with an X, and now go to the left. So now you're in this state here. So essentially you've crossed this X off and you've gone back here. So now you're here. But now what needs to happen is you need to go through those X's that you wrote off. Go through those X's that you wrote off, go all the way to the left, and see that C, and then go through all those A's and B's that you haven't read yet. So go to the left, go to the left, go to the left. And then finally, move, once you see an X, move back, so reset this pattern matching to start at the next symbol that you haven't read, okay? So at this point, there are no transition missing, so I can remove this. Let me just clean this up. So A, B, B, C, A, B, B. So I've crossed this off with an X, I've crossed this off with an X, like this, right? So now I'm here. So now I'm gonna do the same thing. I'm going to cross this off with an X. I'm gonna go through here. I don't have any more A's and B's to read, so I actually can immediately read the C, go to the right. Now I'm going to go through my X's. I'm going to go through here, go to the right with my pointer. Now I'm going to see this B. This is actually going to be the last B that I'm going to cross off. And now I'm going to start going to the left. So I'm going to go to the left, reading all these X's, going back. And at that point, I'm going to read my C, because I'm reading through all the X's that I've already written. So, so that's why at that point, I'm going to see that C, because I'm going to finish this loop. And that at the point that I finish this loop, I'm going to be here. So I'm going to read that C, and then again, go to the left and start reading A's and B's. But in this case, I don't have any more A's and B's. I just have X's. I don't have A's and B's, so I just have X's. So I'm going to use this transition, right? So I'm going to use this transition X. So let me clean this up again. This transition X to go to the right here. So now I'm in neither of these branches, right? It's neither of these cases. In fact, I need a new case where if I'm in Q0 and I see a C, well, I need to go to the right. And essentially the last step I need to do, I need to check that all of these guys on the right half of my string are just X's. So then I can assert that I only have a blank. So that's what I'm going to do. I'm going to make sure that I only have X's here. And then what's going to happen is I'm going to read a blank, go to the left, and then, well, I could have gone to the right just as easily, and then end in a final state, okay? And if I can do this, if I can go through this, so clearly you've seen that I've crossed these X's off. So now essentially what's happened is I'm at this scenario. So at this scenario, I use this branch and I go through all my X's that I've written to end up here for the blank symbol. Okay. Phew. All right. So that was intense. So this is a pretty interesting one, but you do have to see this kind of pattern to make it work. But again, hopefully, well, what's happened is you've noticed that if you do take a long enough string, typically it's enough to make sure that your machine works. Okay. So that's the main takeaway from this is try to solve it this way. Because I find that this might be the easiest kind of way of solving these Turing machine problems. Okay, and yeah, I think that's it. So oh, okay, so I have this tutorial twice. Well, so this is the last tutorial. So instead of to be continued, there's the end. So maybe a few words actually just about what did I want? I wanted to talk about something. Oh geez. No, yeah, I think sorry. Did I want to mention something else? No, so yeah, so no, that's basically it. That was the tutorial on Turing machines. So you're going to see a couple of more topics in lecture. You're going to look at the halting problem. Then you're going to look at sort of the final Chomsky hierarchy with recursively enumerable and recursive languages. Even though I know it's the last week, it's not ideal to have new material happen at the last lecture. It will be important for you to understand those last few sort of lecture slides, lecture decks, and slide decks. So make sure you understand those. Because as you might imagine, they will be, so they will certainly, almost certainly appear in the final exam. So pay attention to that. And yeah, so it's been a pleasure. I hope that you've enjoyed somewhat the tutorials and even more so the course. And again, if you have any questions, you can shoot me an email. And yeah, we'll be organizing a couple of extra sessions, so you can come to those. Maybe we'll bring a couple of problems for us to solve, just for some extra review. But yeah, that's essentially it. So thanks a lot for supporting me. Well, not supporting me, for well, what's the word? I can't find my words. Anyways, thank you for attending the tutorials and for participating, for those of you who did. And I wish you all the best. All right, take care, everyone.